Hello class, Mr. Morris again. This time, this is kind of a backup video. I'm hoping to do this as a class, but if we have any trouble, I wanted to have a backup video that we could use. So we are talking about moles and molar mass in class today. I know this first part is going to be a review, but we're going to get into some new stuff. So let's get started. First of all, NA is what we're going to use to represent this number, 6.022 times 10 to the 23rd power inverse moles. You've probably also seen this written as particles per mole. Same thing. Okay, particles per mole is the same thing as inverse moles, basically. Okay, NA represents Avogadro's number. And that means that 1 mole is equal to 6.022 times 10 to the 23rd power particles. By the way, that extra 2, that's just a more precise version of Avogadro's number. 6.02 times 10 to the 23rd power is going to give you pretty much the same answer. 6.022 times 10 to the 23rd is just a little more specific. So, a particle is a general word that can be used to represent a bunch of different things. I'm not going to write down everything it could possibly ever represent, but it can represent atoms, molecules, formula units. That's what we call a particle of an ionic compound, formula units. It could also represent protons, subatomic particles, protons, neutrons, electrons. It could represent ions, any charged, that's basically a charged atom or a charged molecule, okay, etc. There's a lot of other things. Photons, we'll get into some different ones later, but it can be any particle. To convert moles to particles or vice versa, so going back from particles to moles, the relationship that we can use is 6.022 times 10 to the 23rd power particles equals 1 mole. All right, the molar mass. So this is particles. Down here we talk about molar mass. Molar mass is the mass of 1 mole of any substance. Mass of 1 mole of any substance is called its molar mass. To convert moles to mass or vice versa, from mass to moles, the relationship that can be used is molar mass in grams equals 1 mole of the substance. To convert moles to mass or mass to moles, we'll use that conversion factor. Okay. This is an equation we're going to, I believe that's on the AP exam, that you have that equation to use. You want to be familiar with it, be aware of it. I'm going to zoom in a little bit. I feel like this is not close enough. Okay. N equals M over capital M. By the way, the capital M also represents molarity. That's the most common thing it's used for, is molarity or molar. So I don't use it very often. To avoid confusion, I will use N equals M over MM instead of the capital M. Okay? So N is the amount in terms of moles. So it's the moles. M is the mass in grams. And the M is the molar mass. In terms of grams per mole. Sorry, wrote off the page there. Molar mass in grams per mole. Okay, molar mass can also be thought of as mass per mole of a substance. So we could rearrange this formula so that we have molar mass equals M, that's the mass, over N, that's the number of moles. That'll give you grams per mole, mass divided by moles. So then let's scroll down here a little bit. Atomic mass on the periodic table has two different meanings. Atomic mass represents the mass of one atom of an element. Now pay attention here. One atom of an element in atomic mass units. By the way, that's represented with AMU. Okay, sometimes we call this, some people call this universal. Mass units, which is represented by U. I'm going to use AMU because that's what we've used for like forever, but it's becoming more common for you to see U used occasionally. I don't want you to freak out. I want you to be aware that U and AMU are the same unit, okay? But that's the atomic mass unit. So if I look at the mass of one of our elements, like helium is about 4.00, that means it's 4.00 AMU. Each atom of helium weighs 4.00 AMU. But then we could also look over here. The atomic mass represents the mass of 1 mole of substance. Remember, a mole is 6.022 times 10 to the 23rd power. It's a large number of atoms. It represents the mass of 1 mole of atomic element in terms of grams, which we use the G to represent. All right. Mostly review so far, I think. The mass of an atom of a certain monatomic element is 9.746 times 10 to the negative 23rd grams. What's the identity of the element? What I want you to be aware of is that anytime we ask for the identity of the element, you're probably going to find the molar mass, okay? That's how we're going to identify what element it is. We're going to find the molar mass. Because we can always look something up. We can look up a molar mass on the periodic table and figure out what it is. Refocus real quick. I think that we're out of focus. And lock it so that it doesn't mess up again, hopefully. All right, the mass of an atom is what I'm looking for. The mass of an atom is actually given, is that. So what I'm telling you here, an atom, that means I have exactly one atom. Okay, a monatomic element, that's important. That tells me I just have one atom. Right, both of those things combined tell us one atom, okay? So let's use our formula. I know there are other ways to solve this, but I want to use the formula for finding molar mass. So we have molar mass equals m over n. So molar mass equals m over n is what we're going to use. Molar mass is our unknown, and I want to find that in grams per mole. All right, I have m is the number of grams, and it's given to me 9.746 times 10 to the negative 23rd grams. And then N, I also need N to find the molar mass. N is the number of moles. Now, I don't have the number of moles, but I can do unit conversion to figure out what the number of moles would be. Because I have one atom. This is some data I can use. I have one atom. So I could start with one atom of this certain element. And I'm going to do some unit conversions because I want to find out how many moles that would be. Okay, so I can find moles. So don't forget, if we're going between particles and moles, we're going to use the relationship up here with Avogadro's number. Particles, 6.022 times 10 to the 23rd power particles equals 1 mole. So I'm going to put atoms on the bottom because atom is a form of particle. 6.022 times 10 to the 23rd power atoms equals 1 mole. So I can multiply by 1 and divide by Avogadro's number to find it. 1 times 1 over 6.022 times 10 to the 23rd. Don't forget about the E button. 23rd, not 32. There we go. 6.022 times 10 to the 23rd. And I end up with 1.66 times 10 to the negative 24. We could say 1.661. 661 times 10 to the negative 24th power moles. Okay, that's got me one step farther. What I need to do now is plug in grams and moles to find the molar mass. So molar mass equals 9.746 times 10 to the negative 23rd grams divided by 1.661 times 10 to the negative 24th. See what I come out with. 9.746 times 10 to the negative 23rd divided by 1.661 times 10 to the negative 24th. I get 58.68. 58.68. And then it tells me to identify the element, so I need to take this molar mass, and by the way, in grams per mole, 58.68. I want to find something with about that mass. So I see 58.9, and then I have 58.69. Looks like we have nickel. All right, let's do another one. An element X bonds with F to produce the compound XF5. Okay, this is kind of important, XF5. I have a 0.250 mole sample, 0.2500 mole sample of XF5, and it has a mass of this. Identify element X. Okay, so first of all, I see identify the element, so I'm probably going to have to use molar mass to figure it out. I'm going to go ahead and use that formula. I have moles given. And by the way, that's moles of XF5. It's important to recognize we're not just trying to find the mass of XF5. We want to find the identity of element X. So we'll get around to that. Okay, the mass is 42.48 grams of XF5. And the molar mass of XF5 is what we're looking for. And don't forget this molar mass will be for XF5. All right. Let's go ahead and solve for this. Molar mass equals 42.48 over 0.2500. Some easier numbers to work with. 42.48 over 0.2500. Okay, 169.92. Okay, I'm rounding to 4 sig figs, so 169.9 grams per mole. Remember, that is the molar mass of XF5. I want to know what X is. So to solve that, we need to remember that the molar mass of XF5 is the mass of X plus the molar mass plus 5 times the molar mass of F. Okay, so I don't know what X is. I can't figure that out. But I do know that of XF5, 169.9 equals the molar mass of X plus, and then 5 times the molar mass of fluorine. I'm just going to do 5 times, and the mass of fluorine on the periodic table is, on this one, the AP periodic table says 19.00. Might be slightly different than others. This is the one we use on the AP exam, so 19.00. All right. So I have 169.9 equals the molar mass of X plus 5 times 19.00. I'm going to get 95.0. 95.00. Our molar mass is just subtracting those two. 169.9 minus 95. 169.9 minus 95.00, and I get 74.9 grams per mole. So that tells me the molar mass of X. Let's find something that's about 74.9. Okay, 60 something, 70. Okay, 74.92. 74.9 and 74.92. That's really close. That's arsenic. Looks like we are dealing with arsenic in that case. All right. How many moles of N are in 6.58 moles of NH4NO3? Little bit of a different question. We need to think through what we're going to use to solve it. I'm looking for moles of N, and I'm given moles of NH4NO3. All right, I don't know that we've done a problem quite like this one before, at least not in AP chemistry that I remember. Okay, I don't see molar mass and I don't see mass, so I'm not going to use that formula. This is actually just a conversion problem. So what I need to recognize is I have moles of NH4NO3 and I want to find how many moles of N are in that. So what we're dealing with is the relationship between how many moles of nitrogen we have in each mole of this compound. Okay, so I have 6.58 moles of NH4NO3. For every 1 mole of NH4NO3, don't forget to always cancel your units out with dimensional analysis. We should be comfortable with that. If not, check in with me. Okay. For every mole of this, how many moles of nitrogen do I have? Well, I see nitrogen in this twice. So that means I've got 2 moles of N for every 1 mole of NH4NO3. So I'm just going to do this times 2 over 1. 6.58 times 2 over 1 gives you 13.16. 3 significant figures, 13.2 moles of N. All right, how many grams of AlCl3 will contain 4.31 moles of Cl minus? Well, there's a couple ways we could solve this. I'm going to use unit conversion this time. Okay, you could go ahead and start out by finding, by using this formula. You could solve it using this formula, but I want to use dimensional analysis and kind of some common sense with chemistry to solve this one. Okay, so we're going to start out with what we know, which is 4.31 moles, and make sure you're labeling carefully. That's moles of Cl minus. So I have to have moles of Cl minus on the bottom. My goal is to find out how much AlCl3 I have. So the next logical step would be to decide what's the relationship between moles of Cl minus and moles of AlCl3. Well, I see that I've got 3 chlorides in AlCl3. So there's 3 moles of Cl minus for every 1 mole of AlCl3. I hope that makes sense. If not, jot down your question and let me know how I can help you. Okay. So now we've got moles of AlCl3. I'm looking for grams of AlCl3. So we need to use another relationship. Moles of AlCl3 goes on the bottom. And then on top I need to put grams of AlCl3. Because that's what I'm looking for. The relationship between grams and moles, of course, is molar mass. So if I were to find that out, AlCl3 is going to be 26.98 plus, and then it's Cl3, so we have 3 times the mass of chlorine, which is 35.45. I get a molar mass of 133.33. Now we plug it in the calculator. 4.31 times 1 over 3 times 133.33 divided by 1. There should be a 1 here. 1 mole of AlCl3 has that mass. Get an answer, 191.55 blah blah blah. 3 sig figs would just be 192. 192 grams of AlCl3. As always, double check to make sure your units match what you're looking for. Grams of AlCl3 is all it asked for, and that's what I have now. Okay, that's our first page. Okay, how many K plus ions are in 2.67 grams of K3PO4? All right. Again, we're going to start with what we have. And don't forget to pay attention to what you're looking for. I want to find how many K ions I have. First, we need to go from grams to moles. And then we need to go from moles to ions. But we also need to make a switch somewhere in there from moles of this to moles of the ions. We'll break it down. Okay, so I have 2.67 grams of K3PO4. Okay, I need to put grams on the bottom, which means I'm going to need my molar mass. For K, it's going to be 39.10. And there's 3 of those, so I'm multiply by 3, plus, and then phosphorus is over here at 30.97, plus, and then oxygen is 16.00, and I'm going to multiply that by 4. 212.27. Grams of K3PO4 over 1, or on the bottom, and I have 1 mole of K3PO4 on top. Now I have moles of K3PO4. I'm wanting K plus. So what I would do at this point is, let's go ahead and switch the relationship between moles of K3PO4 to moles of K plus. So for every 1 mole of K3PO4, how many moles of K plus do I have? 3. Got 3 K atoms here, so I've got 3 moles of K plus for every 1 mole of K3PO4. That gets me to moles of K plus. Now I want to switch to ions. So for every 1 mole of K plus, I have ions or particles. So I'm going to have 6.022 times 10 to the 23rd power ions of K plus. Go ahead and do that in a calculator. 2.67 times 1 over 212.27 times 3 over 1 times 6.022 times 10 to the 23rd divided by 1, and I will get 2.27 times 10 to the 22nd. 2.27 times 10 to the 22nd. And my units are K plus ions. I believe we've solved our problem there, haven't we? Okay, move on to how many moles of Ba3PO42 will contain 3.247 times 10 to the 18th phosphate ions. Phosphate ions, that's PO4 with a 3 minus charge. That's what a phosphate ion is. Okay, how many phosphate ions are there here? Well, we've got 2 phosphate ions for every single mole of this. So we've got our relationship there. We got to go from ions to moles of ions, and then from moles of ions to moles of Ba3PO42. Let's get started. 3.247 times 10 to the 18th ions of PO4 minus 3. The relationship between ions and moles, it's particles, so 6.022 times 10 to the 23rd power ions equals 1 mole of PO4 3 minus. Okay, so that would get us to moles of PO4 of phosphate. But I want moles of barium phosphate, not moles of just phosphate. So for so what's our relationship between moles of phosphate and moles of barium phosphate? For every barium phosphate, we have 2 phosphates. So I have 2 moles of phosphate for every 1 mole of barium phosphate. Do the calculations real quick. We got 3.247 times 10 to the 18th times 1 over 6.022 times 10 to the 23rd times 1 over 2. Unless I punch something wrong in the calculator, that gives us 2.696 times 10 to the negative 6th. And that is moles of barium phosphate. All right, next problem says a 2.973 gram hydrocarbon sample containing CH and O are only containing only CH and O are combusted completely with excess oxygen. That means I've got more than enough oxygen, and my hydrocarbon is my excess reactant. The products of the combustion are 1.724 grams of H2O and 4.211 grams of CO2. Now we got to do some analysis because this problem probably seems kind of impossible to solve. I'm going to be asking you what's the mass of carbon in the hydrocarbon sample, what's the mass of hydrogen in the hydrocarbon sample, what's the mass of oxygen in the hydrocarbon sample. Let's analyze it. Let's figure out how we're going to solve this before we even get started. Okay, so what I've told you is I have a compound that's made up of CH and O. So what I can say right off the bat is I have a compound with a formula that looks something like this. I'm putting question marks because I don't know how many of each atom we have. I have CH and O plus O2, which is in excess. I have more than enough of that. So this is my limiting reactant. And it gives me H2O and CO2. All right, that's our first part of our analysis. That's kind of our starting point. All right, the law of conservation of mass tells us that matter can't be created or destroyed. So if I start with a certain amount of carbon, I need to have the same amount of carbon on the other side. If I start with a certain amount of hydrogen, I need to end up with the same amount of hydrogen on the other side, the same mass. Okay? And if I start with a certain mass of oxygen overall, I need to end up with the same amount of oxygen on the other side. So what we need to look at now is where does the carbon go? All of the carbon goes to carbon dioxide. Where does the hydrogen go? All the hydrogen goes to water. And then oxygen's kind of split up, so it's the trickiest one. But what I can tell you is that the carbon in the hydrocarbon has to be equal to the carbon in CO2 on the other side, because mass is conserved. Because of the law of conservation of mass, mass has to be conserved. Okay, I can tell you that H in the hydrocarbon is equal to the H in the only other place I see hydrogen, which is in H2O, for the same reason I just said, because mass is conserved. But oxygen's hard to figure out because you've got all these other places that we have oxygen. But what I do know is I've got the mass of the hydrocarbon sample, the total amount of mass. So the mass of the hydrocarbon has to be equal to the mass of carbon plus the mass of hydrogen that we figured out plus the mass of the oxygen. So I know the mass of the hydrocarbon is 2.973 grams equals, and then I'm going to know those other two. I'm going to know carbon, I'm going to know hydrogen, and then this will be my unknown. Okay. So that's our plan. That's how we're going to solve this. So first, I need to start by going from carbon dioxide. So I have grams of carbon dioxide And I need to find out how many grams of carbon I have. And then down here, when I get to hydrogen, I'm going to go from grams of H2O, and I'm going to convert to grams of H, similar to what we've been doing. So let's get started out. I have, from the problem, 4.211 grams of carbon dioxide. We know the molar mass of carbon dioxide. I can find that by putting mass of carbon, which is 12.01, on this periodic table, plus 2 times 16.00. I get 44.01 grams of CO2. That gives me 1 mole of CO2. I want to know how many grams of carbon there are. So 1 mole of CO2 is also equal to 1 mole of carbon. I have 1 mole of carbon in 1 mole of CO2 because there's no subscript for this. Now I have a mole of carbon. I want to find how many grams of carbon I have because I'm looking for the mass of carbon. So 1 mole of carbon has a mass of 12.01 grams. So 4.211 times 1 over 44.01 times 1 times 12.01 over 1. And I get 1.149 grams of carbon. Now for H2O. The mass of H in the sample, I'm going to start with the mass of H2O, 1.724 grams of H2O. 1 mole of H2O is equal to, if we look at our periodic table, water is hydrogen, which is 1.008 times 2. So H2, and then O is 16 plus 16.00, so it's 18.016. Grams of H2O. Okay, now I have moles of H2O. 1 mole of H2O has how many moles of H? Well, I see 2 hydrogens here, so it has 2 moles of H atoms. I want to know how many grams of H I have. What's the mass of H? So for every 1 mole of H, I have 1.008, because that's our molar mass, grams of H. Now it's just punching it in the calculator. 1.724 times 1 over 18.016 times 2 over 1 times 1.008 over 1, and you get 0.1929 grams of H. All right, I have part A. I have part B. If you'll recall, for part C, the way we're going to figure it out is set this number right here equal to the masses added up. So I have 2.973 grams, because that's the mass of the hydrocarbon. equals the mass of carbon plus the mass of hydrogen plus my unknown, which is mass of oxygen. All right, let's go ahead and combine these. 1.149 plus 0.1929, and I'm going to get 1.3419. I just want to round to 3 decimals, so 1.342. Plus M of oxygen is equal to that number, 2.973. And then, of course, to solve for mass of oxygen, we're just going to subtract this minus that. So we're going to subtract 2.973 minus 1.342. You get 1.631 grams of oxygen, and that is the third part of that question. All right, that's it for our first set of notes. Again, we're probably going to go over this in class, but if you wanted to walk back through it, that's what this is here for. Work on the practice that's related to this. It's moles and molar mass practice. And then after you're done with that, you can look over our next set of notes, which is over mass spectroscopy.